For this lesson, we'll be focusing on a very common terminology in communications, signal-to-noise ratio. Signal-to-noise ratio is defined as the variation between your desired signal, your information, and your undesirable signals, which is considered to be your noise. Now, this ratio is typically presented in decibels as far as units go. However, sometimes your signal-noise ratio can be considered unitless depending on the application. The key element to understanding and calculating signal-noise ratio is knowing how to convert decibels. As a refresher, let's go over decibels. Decibels are a relative unit of measurement used to describe power loss or gain, or in this case, signal-to-noise ratio. Decibels represent the ratio of two values of power, current, or voltage. Now, if you want to convert any of those magnitudes to decibels, the same units of power, voltage, or current must be established, and the reference point, your starting point, must be identified. So I have an equation at the bottom that has a way of converting power to decibels. And on the denominator, I have my power reference, my starting point. And on the numerator, I have the measured power. And that's going to show me how to convert power to decibels. Now, the power reference may change based on the application usage. Now, you're probably thinking, okay, why do I need to convert these magnitudes to decibels? Well, you'll find out later in the exam problems, there are several advantages mathematically to convert decibels and actually calculate using them. Now, in the previous slide, I talked about how you can convert power to decibels, and it's basically 10 log power over power reference. Well, like I also said, you can do voltage and current as well. You just got to change the equation a little bit. Well, instead of 10 log, it's 20 log voltage over voltage reference, and same thing for current. Now, I wanted to provide some visual aids because a picture says 1,000 words, and that usually sticks with people a little bit better. On the left, I have a spectrum analyzer, which shows our power on our y-axis and our frequency on our x-axis. This is usually used if you want to actually get a visual aid of like looking at AM frequencies or FM frequencies or any type of frequency to power ratio. So right now I have my noise floor and then it spikes up with a signal. And then that right there, you can determine how many decibels it is from your signal to noise. And on the right, I have an oscilloscope, and if you zoom in, you can see where the noise is going with the actual signal. And the bigger the noise, the less your signal-noise ratio will be. Hence, on typical applications, you'll use your noise as your reference point. So if some of your equations, you may see 10 log signal over noise. And we'll go over this a little bit more in the example problems. As I stated in my previous slide, since a picture says 1,000 words, let's keep it going. I like pictures. Right now I have 3 different spectrum analyzer signals, and they all have 3 different signal-to-noise ratios. Now your rule of thumb is you want a high signal-noise ratio. You want to be able to put a huge gap between your noise and your signal. So let's start with the first image. The first one has a huge spike. It has a very high signal power compared to its noise, or noise floor in this case. And you'll notice the sine wave is relatively clean. You don't see a lot of noise in there. And on the next one, I drop to my power, and my signal power and my noise floor are getting closer together. In other words, we're having a smaller signal-noise ratio. And that's not as great. You notice the sine wave looks a little bit more choppy. And then on our last one, the signal to noise is actually getting even closer together. It's getting close to hard to distinguish between our signal and our noise. And that's when you have a very low signal-noise ratio, and that increases your distortion. So try to give you a visual aid here of how to imagine your signal-noise ratio on a spectrum analyzer. One last thing I want to mention before we do example problems. When studying, some of your practice problems may actually have it in units of decibel milliwatts, which is dB lowercase m. And this indicates a specific decibel level relative to the 1 milliwatt reference. Instead of having a noise reference, you may see it in the 1 milliwatt reference. And I also supplied you the equations below needed to calculate this. Now also some of your references may actually provide a table where it actually already converts watts to decibels and vice versa. But be aware this does exist. Alright, for our first one, let's start with a relatively easy problem. Right now I have an oscilloscope, and it shows a simple sine wave, and I have my signal, and I have my noise. For this one, we want to determine the signal-to-noise ratio in decibels. So we're going to do it in both. We're going to show ratio and decibels, just because we can. So the first thing I can look at is, what is my voltage, peak-to-peak, peak, or RMS? So I can determine which one. Since I already have my noise in peak-to-peak, I'm going to go ahead and try to find my signal peak-to-peak. The whole idea is you want to find units that are the same. So if you find voltage peak-to-peak for noise, you want to find signal peak-to-peak. And if they had RMS, same thing, you want to find signal RMS. The whole idea is your ratios need to be the same units. So for this one, it's going to be a voltage unit. So I already have noise. So noise equals 0.2 volts peak to peak. So let's find our signal peak to peak. Well, looking at this, it looks like top peak is about 2 volts, and the bottom peak is also about -2 volts. So if you remember the fundamentals, 1, 2, 3, 4, we have 4 volts peak to peak for our signal. So for our signal, it's going to be 4 volts peak to peak. Okay, so that's pretty simple. Well, if you're doing a ratio, all you have to do is put your signal over your noise. So for this one, our signal to noise ratio, this is not in decibels yet, this is just the ratio, is 4 volts peak to peak over 0.2 volts peak to peak. And if we plug and chug that in our calculator, all right, it's going to give us a signal noise ratio of 20. Now this is in a voltage ratio. Now remember, anytime you do a ratios, they're considered unitless. As we look down here, they're unitless. However, you need to know what ratios they are. Well, this one's going to be a voltage ratio. So, which means I'm going to be using this equation right there. Bring this down here real quick. It's going to be decibels equals 20 log, and then I have my ratio, which is 20. So it's pretty simple. And if you plug and chug that in your calculator, it's going to give you an answer of 26.02 decibels. So right now, we just found our signal noise ratio in decibels. So I'll tell you what, I'll put that right here. And dB and 26.02 decibels. Now that's just one way to find it. Let's show you another way, just a proof of concept. Let me clean this up. So we already talked about our voltage is 4 volts peak to peak. Well, let's go ahead and convert that to decibels real quick. So let's go ahead and say decibels equal 20 log, and this one's going to be 4 volts peak to peak, so I'll say 4 volts peak to peak. And if you convert that over, so I have approximately 12.04 decibels. All right, now let's do our noise, same thing. So decibel for noise is going to be 20 log, and for this one we're going to say 0.2 volts peak to peak. And same thing, plug and chug. It's going to give us a negative 13 point, I'll say 98, we'll round, decibels. So if you're going to equate this to a graph, you could say your signal's up here, which is 12.04 decibels, and your noise is down here at negative 13.98 decibels. And we'll say it's 0. So if you want to actually give you a little visual aid here, you want to travel from here to here. We talked about in the PowerPoint, there's a reason you want to convert things to decibels. Because as soon as you convert to decibels, all you have to do is add and subtract. It's pretty simple. So we want to go from here to here. Well, it's pretty easy. If you want to increase this direction, all you have to do is take your signal and subtract it from your noise. And that will give you your signal noise ratio just by adding, subtracting your decibels. So I'll show you. So if you want to look at your signal noise ratio in decibels, it's going to equal 12.04 decibels, and this is our signal, minus our noise, which is negative 13.98 decibels. And that's our noise. That's a simple plug and chug in the calculator method. It gives us a final answer of 26.02 decibels. So that is going to be the same answer as what we had before. So that's kind of why they actually use decibels as a unit of measurement, because once you have everything in decimals, it makes it very easy to calculate. I was able to convert both these to decibels, subtract them, and get the same answer as if I did signal noise ratio. And as usual, the signal noise ratio here was in reference to noise. All right, let's do another problem. All right, for this one's going to be pretty good as well. We're going to determine the noise floor in watts and decibels per milliwatts with the signal noise ratio of 75. This one's going to be different than the last one. This one's already given it in decibels and as well as given our signal noise ratio. So we're going to work backwards and trying to find our noise just based off that. Well, here's the good news. Like we talked about earlier, anytime something's in decibels, all you have to do is either add and subtract to find which one you're looking for. Well, the first thing we're going to do is we're going to write what we know, our signal to noise ratio, is 75 decibels. Our signal, in this case, I'll just go ahead and put, for signal, is already 60 decibel milliwatts. And we want to know our noise. So we know from here to here is 75 decibels. So you want to think that if you're looking this at a scale, you're saying this is a point, and then you're going up 75 to your signal, and that's the next point. So we already know this is 60, and it takes us 75 decibels to get down to noise, which means you're going to take your signal, which is 60 decibels, and that's milliwatts, minus 75 decibels, and that's going to be your signal noise, and that's going to equal negative 15 decibel milliwatts. So right now we already found our noise just by subtracting those two. So I'll just go ahead and put that one right there. It's going to equal negative 15 decibel milliwatts, because all we did was just take our signal and minus 75 from your signal noise ratio, because all it is the gap between your noise and your signal. All right, that was pretty easy. Now we need to find it in watts. So it's not too hard. So let me erase this. So if you look over here, we have decibels, milliwatts, equals 10 log, and this is going to be your power, over 1 milliwatt. Well, we want to find this guy right here. So we're going to have to use the anti-log and work backwards. Well, I also provided the equation in the slide. It's just as easy. So right here, P equals 1 milliwatt times anti-log your decibels divided by 10. So we're going to keep going. So I have P equals 1 milliwatt times anti-log. And now for this one, we said it's negative 15. So we're going at negative 15 right there. And let's keep our units in there. That way it's easy to follow. Divided by 10. Well, that's a simple one. Let's plug and chug that in our calculator. It's going to give us a noise power of 3.162 times 10 to negative 5 watts. So right there, you just found your noise power. And I'll just go ahead and put that right there. Power for noise is 3.162 times 10 to negative 5 watts. So let's go ahead and confirm this. Let me go ahead and erase this. Let's go ahead and try to work backwards and try to use this equation right here. So the first thing I want to do is go ahead and convert my decibels here to power, just like we did for noise. So like we did here, it's power, and this is for signal. It's going to be 1 milliwatt times anti-log of your decibels divided by 10. So if I plug that over here, it's going to be 1 milliwatt times anti-log, going to be 60 decibels divided by 10. And then plug and chug that one. It's going to give us an answer of, that way you can see what I did, 1 kilowatt. Let me go ahead and clean this up. Now we have our signal to noise, which means we can plug and chug it in this guy right here to find our signal noise ratio in decibels, just as a confirmation. Decibels equal 10 log. It's going to be our power over power reference. Now typically, like we talked about earlier, your power reference is your noise, which means your equation is going to look something like this. Log over signal to noise. Now we already found our noise and power, so we can just plug and chug this down here. It's decibels equal 10 log, and it's going to be signal, which is 1,000 watts, over our noise, which is 3.162 times 10 to the negative 5. And if we plug and chug that in our calculator, it's going to give us an answer of 75 decibels. So right there, you just confirmed your answer, because we have a 75 decibel signal noise ratio from our noise to our signal. So that confirms our answer. Let's do one last problem. Last problem here, we're not really going to focus on the signal noise ratio per se. This one's to reinforce the concept of decibel conversion. So for this one, we need to determine the output power for the following transmission system. Now we have an input of 5 watts, and it's going through this whole system, and then we want to know what the output power is. Well, the good news is this was already supplied in decibels. It's very easy to add as subtract or loss just based off what we see here. So we're going to show you the hard way first. So the hard way is we go and convert each stage just using our conversion over here. Now the way we're going to do this is we're going to use this guy, but we're going to find the reverse of this guy, which means we're going to find our power over power reference, and then it's going to be our anti-log of your decibels divided by 10. So for this one, it's pretty simple, and we'll go, like I said, we'll take it one at a time. So we want to find our power right there. So we have 5 watts, which is going to be our power reference. So it's going to be P over 5 watts equals 10, which is our anti-log, and our decibel is going to be 5 divided by 10. So if I continue on with this guy, it's going to be P over 5 watts equals 3.162. And what we're going to do is multiply 5 times this guy, and that will give us our output power. So P equals 5 watts times 3.162. That's going to be approximately 15.8 watts. So that one's going to be 15.8 watts. Okay, now we're going to do the same thing. We're going to go and try to find the output power right there. So same thing, I'm going to erase some of this. And same thing, I want to find P over our reference. Now our reference for this one is going to be 15.8 watts. 15.8 watts equals anti-log. Now for this one, it's going to be 30 decibels. And you basically have to take this one step at a time. And same thing as earlier. P over 15.8 watts equals going to be 1,000. And same thing, I want to multiply 15.8 times 1,000, which is pretty easy. I don't need a calculator for that one. It's going to be 15,800 watts. So right there, I have 15.8 kilowatts. And now it's being transmitted over the air, and we have a 0.2 decibel loss for each mile. So let me go ahead and clean this up a little bit more. Now this is pretty simple math. So you want to determine your decibel loss between this antenna and this antenna, which means it's 0.2 decibel loss, which is considered negative anytime you have a loss, per mile. Well, we know we have 100 miles. So if you want to find your decibel loss, it's going to be decibel over mile times your mile. So when you multiply those together, they'll cancel each other out, which means it's going to be 0.2 decibels per mile times 100 miles. And that's pretty simple. That's going to come out to be a negative 20 decibel loss, because like we said, anytime you have a loss, it's a negative number. So that's pretty simple. So we know our loss right here is negative 20 decibels. All right, let me clean this up. And we're going to do the same thing again. We're going to say our power over our power reference. For this one, it's 15.8 kilowatts equals anti-log. Now for this one, it's going to be a negative 20 decibels over 10. And if you plug and chug this in your calculator, it's going to come out to be power over 15.8 kilowatts equals 0.01. And if you multiply those together, and I'll bring it down here, so it's going to be P equals, and again, we're going to multiply these two together, which is 15.8 kilowatts times 0.01 equals 158 watts. So right there at this antenna, it has received 158 watts. All right. Well, from here to here, there seems to be a 0 decibel change. Anytime there's a 0 decibel change, there's no point in actually going through this calculation, because anytime you have a 0 decibel over 10, it's going to be 0. When you have an anti-log of 0, it's actually going to be 1. So this whole thing right here would equal 1. 1 times your reference. So this guy right here is going to be the same as your input. All right. All we have left now is our output audio. So let me go ahead and clean this up, and we'll do this one last time. So we're going to have P over our reference, which is 158 watts, equals 10 anti-log, and decibels negative 10 over 10. This is going to be easy. And of course, I'll bring this over here. P over 158 watts equals anti-log of negative 1 equals 0.1. That's pretty easy. And again, we're going to multiply both sides here. So we're going to have P equals 158 watts times 0.1. And that's going to give us a final answer of 15.8 watts. So right now we went from start to finish and found our input and output of each one of these. And it's 15.8 watts. I'll put that right there. So we just found our output in power. So let's now do it the easy way. Now that it takes a fraction of the time. So I'm going to clean this up. The good news is anytime your system or anytime you're doing a calculation that's already in decibels, you just add them all together. For the first one, it's going to be 5 decibels plus as a gain, so it's going to increase, so it's going to be 30 decibels minus, because we have a loss, anytime there's a loss, it's a minus, 20 decibels. And then it's going to be plus 0 minus, and this is going to be a negative 10 decibel loss. Anytime, again, negative is a loss. And we're just going to add all these together. So your whole network here, your whole system, is going to have a grand total of a 5 decibel gain. So anytime you have a 5 decibel gain, that's pretty easy. So it's going to be 5 decibels equals 10 log. And we want to know what our power is over our power reference, which our power reference is 5 watts. And we're going to do the same thing we did earlier, but instead of doing stage by stage, you went ahead and added all these decibels together, so it makes it easier on yourself. So now it's going to be, and I'll just bring it over here. So it's P over 5 watts equals 10, which is your anti-log, and that's going to be decibels over 10. It's going to be 5, of course. So it's going to be P equals 5 watts equals 10, and this is going to be 1/2, so 0.5. All right, so that's pretty easy. So it's going to come over here and be P equals 5 watts. This is going to be 3.162. Now this looks similar to this first guy right here. Multiply these two together. It's going to give us a final answer of P equals 15.8 watts. Instead of going through the long process, I could have added all these together, just because anytime you have something in decibels, you either add or subtract. There's a lot less math involved. And then I actually came up with the same conclusion as I did it the hard way, and it took me a fraction of the time. Hopefully this is enough practice here to get your feet wet as far as understanding signal-to-noise ratio and how we convert to decibels and get in and out of decibels. Because if you're able to master that, signal-to-noise ratio is very easy to understand. So if you have any questions, feel free to let me know, and I hope you all have a good day.